if you wanted to actually use the other handheld mic, then go ahead and use that. I think you should be good.
So this one.
Check, 1, 2.
Be recorded or no?
No, both of them are recorded.
Both of them are
There's
recorded.
one.
I see. Okay.
Should be all set?
Yeah.
All right, perfect.
Thank you very much. Okay, let's get started. Can you guys hear me? Good? Okay, great. Welcome back. So today we will keep talking about the background. Hopefully we finish that in half of the class. Then the next half we are jumping into hacking. We will say the first vulnerable program and how do we exploit that. So we will look at a buffer overflow, a very simple one. So next week we're looking at more difficult ones. So we start with buffer overflows and more difficult ones. So first half of this class, we talk about more background, system call, environment variables, some tools you were using in this class, and the ELF file format. So you don't have to remember all of this. Like I said, there is no written exam. So the exam is only CTF. So all of the information, you can look them up when you need to, but we still need to go through them so you understand what's going on. Okay, first of all, system call. So if you took operating system class or maybe also 220 systems programming, you probably already know what is system call. So system call, there are a lot of system calls. System calls are the interface an operating system provide for the applications. So the application runs on unprivileged level. The operating system runs the privileged level. So privileged level, unprivileged level, there are different modes of a CPU. So in privileged mode, the CPU can't do anything. Unprivileged mode, there are a lot of restrictions. So for fault isolation, security isolation, that's why your applications, when you run application, the application runs in unprivileged mode. The OS runs in the privileged mode. So when the application needs to do something dangerous, needs to do something fun, it will ask for help from the operating system. And the operating system provides a system call interface to do that. Last class, I showed you guys there are some instructions in x86, call instruction to make function calls. So when you want to make a system call, you do not use the call instruction. There are two more instructions you can use. In 32-bit, we can use int 80. In 64-bit, there is an instruction called syscall. We can use that. So when a system call happens, the application calls a system call, then the CPU transitions into the privilege mode, the kernel gets start running, the kernel do a lot of services, then return to the application. So in some sense, the kernel is doing something on the behalf of the process, okay? So usually, if you are a C programmer, you are a Java programmer, you do not directly make system calls. C programmers, you make system calls through C library. Java programmers, usually you don't directly make any system calls. But in this class, we are going to write a little bit assembly code to do system calls. I will show you in a minute. So there are a lot of system calls in Linux we are using right now. There are probably more than 400 system calls. Some of them you are familiar with. At least at the C level, you're probably familiar with. When you open a file, when you want to read a file, what do? You first open a file, then you read it, then you write something there. After that, you are done, you call the close, right? So usually what you are calling, those are library functions, but those library functions are just the wrappers of the system calls. Eventually, those library functions, they will make the system call. Other operating systems, they may have even more system calls. Windows have like 700 system calls. You don't have to remember those. You just, when you see those system calls you are not familiar with, just Google, like everything else you do in this class. You just Google. We just quickly go through those system calls I listed here. For example, open is to open a file. Read is to read from a file. Write, close. Wait is a system call for a process to wait another process to exit. exec, that is creating a new program. We're going to use a lot of this one. Fork is to clone another process. It will be the same process you are running. Exit is a process to quit. Kill is for one process to send the signals to other process. That's called kill. So, like I just said, C library functions, usually they provide a lot of wrapper functions for system calls. So the system calls I listed here, I think all of them, they have a corresponding C function. They have the same name. The C library function is also called open, so you can directly use a C function. When you write a C code, you can directly call that open C function. In the implementation of the library, eventually there are hand-coded assembly to make system calls. There is a tool we can use to trace what system calls a process is making. That tool is called strace. It's very easy to use it. Just strace the program you are using, then you can trace the system calls you are using. So let's go to our platform. So this is our platform. We just run any challenge. Doesn't really matter here. We run this challenge. For those who do not understand how we run this challenge, you click the challenge, you click Run Challenge. What happens when you click this is under the hood, we will create a Docker image specifically for you. Well, you can SSH into that Docker image, but you don't have to, okay? You just close this dialog, then you just click here, the terminal. Then we have a terminal directly for you to that Docker image. You can SSH into that if you are more familiar with terminal. You want to collect from your local terminal, you can do that, but you don't have to. Okay, so we are here. I'll make it a little bit bigger. So we have a program ls. We also have this program and32, right? So you run this program, those program runs. So you want to figure out what system call those programs has been making, then you can use strace, then you can call our program. You can run our program. Then this program, the strace tells you what system calls this program make. You can see the first system call recorded here is execve, that's create a new process. After that, you can see there is strace, there is access system call. That checks if this access checks if this file exists, and it returns this file doesn't exist. Then there is a break system call. If you took OS class, you know the break system call is to set the break between heap and stack, something like that. So basically, this is change your memory layout. Then there is some architecture protection control system call. I don't remember what this is for. Then there is a file control system call. Then two more access to check if this file exists, check this file exists. When there is a memory map to load something from the file into a memory. Also, there is open at. This is very similar to open. Okay, we always say the open system call. This is open at. They're basically the same. It's just specific telling the OS I'm open at some location. So using this tool, strace, you can see what system calls your program makes. And obviously, this program, you guys already saw the program. This is a very simple program. We add two integers together, print out. That's it, right? So it's like I wrote this program. I only wrote the main function, right? The main function I wrote doesn't really make those system calls. So those system calls up from actually everything from here. Those are just the standard system calls the loader used to set up the environment for the process. The real system call my program make is this write system call. That's because I have a printf. I printf the results of the addition of two integers. That printf eventually print out to the standard out. That's why we have a write system call. So printf eventually calls write system call to write to the file descriptor 1. So in Linux, file descriptor 0 is std in, standard input. File descriptor 1 is std out. File descriptor 2 is std error. So all of them actually map to the terminal I'm using here. Okay? So in this example, you can see we're only making one system calls. We can also do a strace on ls. You can say the ls makes a lot of system calls. Some of them also are standard, just loading libraries. First one, execute the program ls, then check where is the break, then finding some libraries, trying to load those things. So strace is a tool you can use to quickly understand what a program does, especially what system calls it makes. There is a similar tool called ltrace. L means library. It can trace what kind of library calls a program make. So in this class, we are going to learn how to make system calls at the assembly level, because those libraries, like I said, basically they hard code those assembly to make system calls. System calls, basically, they are software interrupt. And there are two types of software interrupt. One is called exception. Another one is through exception. Another one is through some special instructions. Exceptions is when something error happens. For example, if your program have a divide by 0, the computer doesn't know how to handle that, so the CPU will throw an exception. So the OS will handle that. The software handle that because the hardware doesn't know how to handle that. Then to make system calls in x86, what we do is there are two instructions. One is an int instruction, but in Linux, we specifically use int 80 in hex to make system calls. Int is just to raise an interrupt. And the interrupt has an index. We use index 80 for system calls. There are many other interrupts, but this one is specific for system call. For the 64-bit Intel CPU, they introduce the system call instruction. The instruction is just called system call. Okay? We will see how they are different. So like I said, there are hundreds of system calls. You don't remember all of them. I don't remember all of them. So if you want to find out what system call you need, you just Google this. I give you a link. This link lists all the system calls in x86 Linux, in ARM, in 64-bit Linux. Those system calls, let's say this one. The picture I have here is for 32-bit system calls. And the first column has the system call numbers. When you make a system call, you actually put the number into the register EAX. They have a percentage sign here. That's because they are using the AT&T syntax. In our class, we're using Intel syntax, so there's no percentage sign. Anyway, you put the system call number into register EAX. And the first one is just reset. Then there is exit, fork, read, write, those system calls. And for those system calls, there are parameters. When you want to open a file, what do you need to specify? You want to specify which file you want to open, right? That's at least one. Or what kind of permission you want for this file. That's why, let's say, the open system call, the first argument is a pointer to the file name. And you are supposed to save that into the register EBX. Then there is a permission where you need to put that into ECX, mode into EDX. For just to read files, you can set those two as 0, then you will be able to read. So this is for 32-bit Intel Linux system calls. So next, we are going to look at this piece of assembly code and try to figure out what this is doing. This piece of code is actually called a shellcode. It's only 10 and this is what hackers use to get a shell. Okay. Here I have the ASCII table here, so we can figure out what it is. Let's say the first instruction we have is exclusive OR EAX. When you do an exclusive OR on the same register, what do you get? You get 0, right? So basically what this instruction does is to set EAX as 0. That's the purpose. Then the second instruction, you push EAX onto the stack. So here we have this, let's assume this is our stack. I always draw the high address at the top, the no address at the bottom. The stack goes from top to bottom, okay? The stack goes down. We assume the stack top right now is here. So ESP, that's the extended stack pointer, points to here. So the next step is we push EAX. So what will happen? The value inside EAX will be stored onto the stack, which is 0. So this 4 bytes here now will be 0. So ESP points to 0, which is 4 bytes. Then we push another 2 things. Well, those looks like random numbers, right? That's a little bit weird. We push those 2 things there. So anyone can guess what this is? This is 4 byte, and there is a 0. So those 9 bytes, what are those? This is actually a string. Yes, that's a system call parameter, but which parameter? This is a system. This is a file name you are trying to, the program name you are trying to execute. Yes, it's a bin sh. Yeah, in this case. So that's why if you go back to the ASCII table, you will figure out. Let's say we have 68 here. You go to the ASCII table. This is hex numbers. 68 is here is H. Okay. So the whole thing is actually just the / bin sh. Okay. So basically that's a program we are trying to execute. So after that, we move ESP. So ESP points to what? ESP points to the string now. That's a string / bin / sh. Now we move the value of ESP into EBX. Then we push EAX again. EAX is still 0, so we get another 0 on the stack. Then we push EBX. So the address of this string is also on the stack. Then we move ESP to ECX. So ECX points to the address of the string and a 0. Then the last step, we move B to AL. Remember, AL is part of the register EAX. EAX has 32 bits. The lower 16 bits called AX. The lower 8 bit called AL, right? So EAX is already 0. We move the B to the least significant 8-bit, makes the whole EAX also as B, okay? So what is EAX again? That's the system call number. And we have B, which is this one. So we are going to execute the system call EXE-CVE. That is a system call to replace current process and have a new process. And the new process name is this part, which is bin /sh. Then we make the system call use int 80. So that is our first share code and also the first piece of assembly to make a system call. So if you look at the C library for the same system call, you can find this is its prototype. EXE-CVE, first you have a file name, then you have the argument for that program, which in our case we don't need to give any argument. Then you can provide an environment variable for that. In our case, we do not want to provide environment variable. That's why the EBX points to this string. EDX, we just said it was 0. ECX will be the address of that string and 0. So we are basically, this piece of assembly is equivalent to the save function call like this. to create a new process. If you do not know how to use any specific, say, function call or even system call in a Linux terminal, what you can do is you just do man. You do man exe cve. It tells you how to use this. So here you can say, it says exe cve, then there is a 2. That means this is the chapter 2 of the manual, and chapter 2 of the manual is for system calls. Let's say we have been using the tool ls, right? ls is a command. It's not a system call. A command means it's most of the commands, they are a program. Some commands are not. For example, cd is not really a cd change directory. It's not really a program, but the ls is, right? So if you do man ls, it will show you how to use the command ls, and also you can say here, one is, it says it's in chapter 1, because chapter 1 is for command, chapter 2 is for system call, chapter 3 is for C library, I believe. Let's see. For example, what C library function you can think of? What did you say? String length. Okay, let's do string length. When you do a mass string length, you get to say the prototype of it, how to use it, sometimes some examples. And it also shows you this is chapter 3, because chapter 3 is a function, is a library function, okay? Okay, that's basically how we make a system call at a 32-bit machine. Things are quite similar at a 64-bit machine. Somehow the system call numbers are different. I don't know why they designed this way. 32-bit of system, a lot of system calls are same as a 64-bit, but the system call number are different. In this case, read has a number 0 now. And the parameters are also very similar. However, we are using different registers. Previously, we are using EAX for system call number. Right now, we are using the 64-bit version, which is RAX. That part is the same. But the second part, previously we were using EBX or EDX. Right now, we are using RDI. Okay? You don't have to remember this. You have to develop something like this. Just look up for the tables like this. Okay, you don't need to remember this. So this is an example of the 64-bit version. We are getting the same shell, bin sh. By the way, you notice that here, the bin sh, I'm using 2 / here. Why I have 2 / Anyone can guess? What? Not really. That's a good guess, but not really. For example, here I didn't escape, right? So in Linux, it doesn't really matter how many slash you have. It doesn't really matter. Let's see. We have here, let's say we want to go to, so where do you think I'm going? Changing the directory. I'm actually, so 1/ is root, right? 1/ is root. Multiple / the same thing, it's still root. So in Linux, doesn't matter how many / you give. So say I'm still here, root. So let's say, do we have a code here? Yeah, we have a code here. So let's say, let's do something like this. Can we still go to code? Yes. Okay, no matter how many slashes you have, Linux will consider that's a 1/. That means you can use that as a padding. So the reason we have 2 slashes here is I just want to make this 8 bytes. So I use a slash as a padding here. So let's say this piece of code. First of all, we still want to use a system called exe cve but the system call number has been changed. In 64-bit, it's 59, not B. B is what? B is 11, right? So now it's 59. Then we first push RAX. We create a 0 on the stack. Then we change RDX to 0, RSI to 0. We move this string's address to RBX. We're not really moving the string to RBX. We're moving the string's address to RBX. Then push that string's address onto the stack. Then we also push the address of that string's address to the stack. Then we pop EDI because here we already pushed that address here. So basically this instruction does is we are moving RSP to RDI. The reason we're not directly doing the moving is probably we don't want the instruction to have a 0 or something. We can do that. Sometimes in our shellcode, we do not want to have a 0. Then we move the system call number to AL, then we make the system call. Okay? So that is what happens in the 64-bit, similar on the 32-bit. So if you want to learn more about system call and how Linux programming, I recommend you this book, Linux System Programming. This is probably the book you use in 220. I'm not sure. Okay, more background here. Environment variable and share variables. I think most of you probably already used the environment variable at some point. Environment variables, they are just named values. There is a key, there is a value, and this is how you give some information to a new process you want to start. And you can set environment variables in the terminal, and the syntax, very simple, just the name of that environment variable, equal sign, and the value of that. It can have several values, multiple values. For example, pass. We always use pass. So in this Linux system, we have an environment variable called pass. We want to see its value. We do an echo, $sign pass. It will show you all the paths of the system. So when I type ls, when I type something like ls, I'm not really specifying where is ls, right? So the shell will look at those folders and try to find the first matching program ls. So you can say in this example, the path environment variable, it has multiple values, and they are separated by this semicolons. So the name of the environment variables, they are case sensitive. That's something you need to pay attention to. Environment variables, they are system-wide. They will be inherited by the child process, also new terminals. And there are share variables as well. They are only specific to share. In our class, we will mainly use environment variables. So in the server we are using, we only have bash there, I believe. On my local computer, I use ZSH. So for example, this is my local computer, and I use ZSH. You can see it's more beautiful than the terminal we have on the server. We tried to install that on the server, but the TA couldn't get it done right now. Well, we're still working on that. There are some popular environment variables. You don't have to remember them. For example, user, home, shell. Those are the ones we can use in our server. For example, this is our server. You want to figure out which shell we are using. We just do an echo shell. It tells us, oh, on the server we are using bash. On my local computer, we do an echo shell. And you can see I'm actually using ZSH here. You want to say who is the current user, you can do who am I. Also, you can do echo user. It tells you who is the current user. Okay. several commands to help you set environmental variables and also display environmental variables. env, this one, just to print out all the environmental variables. There are others, set, export, those kinds of things. You don't have to remember that. At some point, we're going to use them. So, like I said, environmental variables can pass the value to a new process. You set some environmental variable in a shell. You create a new process. The new process will be able to see that environmental variables. But how is that achieved? How is that implemented? So what actually happens is we saw this memory map last class. This is a 32-bit machine Linux memory map. The top 1 GB is reserved for Linux kernel. Then we have the stack, which goes down. So what happens is that when the loader loads your program, before it loads your program, it will also load the environment variables, all of them, to the stack. So it's at the very top, actually it's the very bottom of the stack, right? You will put the environment variables there. So to show you that, we can just debug a program on the terminal. Let's say we debug a simple program. GDB, we use our AND32 program. In this class, we are going to use a lot of debuggers. So get yourself familiar with GDB. I prefer to use those terminal tools because by using that, you can really learn what's going on. In this class, I don't really want you to use more advanced tools. For example, when we get a disassembly, we just use obj dump in the terminal. When we debug a program, we just use a GDB in the terminal, because that helps you to really understand what's going on. If you use those fancy tools does a lot of tricks for you. So you do not really say under the hood what's going on. Okay? So there are a lot of GDB commands we are going to use. I made some slides there. We will briefly talk about that, but it's more about you need to practice. You need to do those things by yourself. So we debug this program. Now this program is loaded. Now let's say we set a breakpoint at the main function. We use B, which is set breakpoint. The main is a function name. We set a break here. Now the breakpoint is set. Then we want to run this program. We just do R, means run. So now the program is running. We are actually in the main function. If we do a disassemble here, we can say this is a disassembly of the main function. That's not what I want to show you right now. So what I want to show you is the environment variables is already on the stack of this program. So where do we find the stack? Which register should we go for? Which one? ESP, okay. So there is a command we can use is exam. X means exam. So we want to exam maybe, let's say, 50 strings at the address of ESP. Let's see if we can find the environment variables. No, we do not find them. Then we can exam more. So here, we find the address is ESP. Then when we examine this, we're going to higher address. Higher address where some data pushed there before the main function was executed, right? So let's say we do this. Still no. See? Those are the environment variables. So all the environment variables, you can say those ones. There are probably not many, maybe 10 environment variables. They are already pushed onto the stack. They are actually in the address space of the program. So if we get out here, we do an environment variable, you can say those are exactly the same thing, right? Those were pushed onto the stack of the program. So those are environment variables. Why do we talk about this? Because this gives us a way to inject some data into a process address space. you can inject something malicious there. We are going to use that technique later. Let's quickly talk about what ELF file is. ELF stands for executable and linkable format. So this is the format, standard format for Linux executable files and also object files, shared libraries, even core dumps. So core dumps is something when your program trigger an error, the OS kills the program and the OS try to dump the memory of the program so you can debug what's going on. So that's called the core dump. So some of you are Windows users, so you probably don't know for Linux, the file name extension doesn't really matter that much as in Windows. So you can say a lot of different extension names for ELF files, like AFX, that's usually for embedded systems, that's like for firmware. Bin file, obviously that's just binary. Then you can also say ELF sometimes. .o, that's object file. KO, like a kernel object file. Mod, probably a kernel module, something like that. SO, shared object file. But that doesn't really matter that much. They are all ELF files. They all have the same format. So the ELF file, which is the program you have is an ELF file. It contains program, which means code. It also contains some data for it to use. And also this file format describes how this program should be loaded into memory. It also has all kinds of header information, which we are going to take a look at. So let's say this is an ELF file. The ELF file, any ELF file, they mainly have 4 parts. One is its own header. We call it an executable header. Then there could be optionally program headers, sections, and also section headers. Let's say, so the executable header looks like this. This is a data structure. You don't have to remember this, obviously. Something is at the beginning of that, it's always, there is a 4 byte of magic number, which is a hex 7F and also ASCII ELF. That 4 bytes are always there, just to tell some tools, this is an ELF file. That's just the magic numbers. Then it also has a type field to tell you whether this is a statically linked executable, this is a library function, or this is some kernel modules. And it also has a machine field to tell you this ELF file runs on x86, 64, or ARM, those kind of things. There's a tool called readelf to help you decipher this. So what we can do on the server, let's go to the server. Let's first use XXD. XXD should use a binary of a file. So we do a XXD, we do a, what is the name of the program? And 2. Oop, this is big. Should I do a head? Yeah, this is big. Let's do a head here. Okay, you can see this is the beginning of the program we have been using, the 32-bit version of AND. And you can see at the beginning, it has a magic number, 7F, then the ASCII ELF. That's just a magic number. All the ELF file has that. Then after that is just binaries. Binaries we do not know how to read, right? So that's why there is a tool called readelf. If you use a header 1, it shows you, it deciphers that. Readelf. It deciphers that, the header of the program. For example, this one, we can say this is a Unix program or Linux program, doesn't matter. This one runs on Intel machine. Some other header information there. So like I said, the code and data in an ELF file, they are logically divided into different sections. And the main purpose of this is for linkers and loaders. They will check those information so they know how do I link different object files together, how do I load the program into the memory. This is another header of that. We're not going to go through the fields one by one, just to pay attention to the attribute here. So the sections, can have different flags. For example, the section is writable. The section has to be allocated. The section is executable instructions. EXEC, INSTR, executable instructions. So it tells you what this section is. Let's skip this. So if you use readelf, you can get all the sections of a program. Let's say this is an AND program. We get all the sections. So some of the sections maybe you can recognize. We talked about them a little bit last class. Right, first of all, this one, .text. That is a section to store the code you write. As a C programmer, you write a main function, you write other functions. Your code usually go to this section. There is an init section. Those are some C library functions. Before your main function executes, the C library function executes, right? Those are stored here. So after your main function finishes, the C library function takes over and do some cleaning, and that is in the finish section. And those sections you can say there are program bits. Their type is program bits. So those are code. Since they are code, they should be readable, executable, but not necessarily writable, right? That's why you can say their flag here is A, I think it's read. X means executable, but no W here, right? W means writable. Some of them, those are W, writable, okay? Now other sections, let's say the data section. If you have global variables, that will be in the data section, and this one is writable, okay? Then uninitialized global variable is in BSS section. It's also writable. There are many other sections like the interpreter, that's to load the interpreter. There are some sections related to security like the PRT, GOT, where we'll talk about them soon. Also, there are symbols, there are strings, they are in different sections. So there is a technique we are going to talk about. Is called the lazy binding, and that is a technique used in all modern loaders, modern OS, but that is something we can exploit. So we will quickly go through them here. So when a binary program in a hard disk is loaded into the memory and become a process, the dynamic linker or loader will actually resolve the reference to some other library functions. The reason is you develop a program, someone else develop a program, you run the same program in one machine. Both of your program use C library, libc. So one way to solve this, one way to do this is the operating system can load 2 copies of libc into the memory, for each of your program. But this is obviously a waste of memory, right? So modern system, what we do is the operating system will only load 1 copy of libc, and no matter how many copies of programs are running there, when they run libc program, they are calling into the same libc program. But the problem is each program has their own address space, then as a virtual address space, and that address space can't even be randomized. So the libc address, the virtual address, will also look like randomized to them. So how do they know what is the address? That's why there is a loader, when the OS loaded the program, there is a dynamic link process to resolve the reference to those functions, to those shared libraries. So because at compile time, you don't know where are those functions. Only at the load time, the OS will figure out where are the functions and tell the program those are the address of those functions you are going to use. So, but another thing is, the C library is big. You are a C developer. You're not going to call all the functions in the C library. You're going to call some of them, sometimes just one of them, right? So the OS doesn't have to resolve all the addresses. If the OS resolves all of them, it's also a waste of time because 90% of them will never be used. So the OS, the loader, not necessarily the OS, the loader uses a technique called the lazy binding. Only when the first time your program make a function call to that function, C library function, the loader will try to figure out where that function is. If your function never make a function call, if your program never make a function call to another C library function, your program never find out where that is. It doesn't have to figure out. And this is achieved by some technique called the procedure linkage table and the global offset table. You don't have to remember these names. I will show you one demo how it works. Let's say this figure actually tells us how it works. Let's say this is your program, and your program is going to call the C library function called puts. So what happens is this is dot text region section, which has your main function. Your main function calls puts. Even if you do a printf, eventually it will call a puts. So then the puts will go to the PLT table, and the PLT table has just those instructions. And to look for the puts address there is another table called the global offset table, GOT PLT table. And at that time, this address is just a dummy address for all the library functions. This is a dummy address. It's not a real put address. The dummy address points to a start, which looks for the function, looks for the address of the function you want to call. Okay? So which means the first time you call this, you actually trigger the loader to find the function. But after that, that address will be put here. So the second time you call the same function, it will directly go to that address instead of go to the stop to look for that address. So I can quickly show you this on our server using GDB. We have a function. We have a program for you called lazy B. Okay, it's here. Lazy B. You run this program. I'm not showing you the source code of lazy B, right? I should show you the source code. Let me see. Where's the source code? Okay, so here we have the source code of this function, this program. Super simple. There is a main function. In the main function, we call the printf, which is a library function, twice. I want to show you that the first time we call this library function, it will be slow. It will go through the loader. The second time we call the printf, it will be fast because it already knows the address. So this is a source code. Then go to our server. What we do is we do a GDB. We do, what's the name of this? Lazy32. We set a breakpoint at the main. A little bit smaller. So now we have a breakpoint here. So let's say, we need to run this program. Then we can disassemble. So you can see that the printf becomes the printf becomes puts. So there are two different calls to puts. That's it. That's how big this program is. Let's set two breakpoint here. this is the address of the first put. When we set a breakpoint, we just do B. Because this is the address, we use a star there. Then we set the first breakpoint. Then second breakpoint, we copy this address again. We set B, start this. Okay, now we have 2 breakpoints. Then let's do a C, which is continue. Now we run this program. Now we are about to call the first puts. We're about to call this. So we want to see how it works. So we want to go into this. So we use the command SI. S means step. I means instruction. So we are going to step 1 instruction. So we are going into the function puts. As you can see, this is where we are at. We are at the jump. There is an indirect jump here. Remember, when we do SI here, we get into this place, okay, right now. Then if we do several SIs, you can say we go to this function which doesn't have a name. That is actually the loader function to load what's going on. If we really want to say the instruction here, we can do exam 20 instructions at EIP here. And you can see those are the instructions here. It probably ends somewhere here. So, but those are the instructions. That's the first time we call puts. Now I'm going to use say continue. Now we are going to the second call to puts. Okay, I'm not cheating here. See, we're about to call the second time. We're going to puts. But this time we do SI again. We are still here, but if we go to a little bit more, one more instruction. Okay, this indirect jump. Last time we jump into a unnamed function, which is this. This is an unnamed function. That is a loader's library to load the address. And the second time we call it, we're not jumping to an unnamed function. We're really jumping into the say library function puts. Okay? So this time, actually, we're going to call puts. Okay? So this shows you how lazy binding works. I give you some cheat sheet here for you to just to practice how to use GDB. By the way, on the server, we do not have all those fancy GDB plugins. The TA couldn't get it installed there. For example, I'm on my own laptop. If we do a GDB lazy program, let's break a main. Then we just run. You can see my GDB here has all kinds of plugins to show you the code, to show you what the stack is, whatever. The GDB on the server, we don't have this, but it has. That's why you need to be more familiar with those commands. Okay. Well, also, if you feel you have a spare time, you can help us install this on our server. You are also welcome. Okay, let's skip this segment saying I don't want to bother you with those details. Another background you guys need is manually do a lot of binary analysis. So I've been showing you a lot of tools. You need to get familiar with those tools throughout the semester. That's the tools we are going to use. File tells you what file this is. Readelf help you to say the headers of an Elf file. Strings just to show you the human readable strings in any file. NM shows you the symbols in a file. We use obj dump a lot to get the disassembly, GDB a lot to do debugging. There are more advanced tools. The one a lot of hackers use is called IDA Pro. This one is like the best disassembly tool, also this compiler tool. It has a free version you can use. The commercial version is very expensive. Several years ago, I bought a commercial version for my lab. We have just one floating license, cost us $20K, more than $20K. Well, it supports Intel and ARM. Our research we do ARM. Yeah. Then 2 years ago, maybe there is a NSA published their tool called Ghidra. This one is actually very good. It's totally free, open source, and we have been using this one a lot. It has decompiler. Decompiler means from disassembly, it generates C code for you. Sometimes when a program is too big, reading the disassembly is very difficult. That's why you want to decompile it to C to better understand. Also, there's another tool called Binary Ninja. This one has a web version. You can just register account on web. They all have free versions. Ghidra is totally free. Binary Ninja, the web version is free. You can also use that. But I still want you guys to use as much OBJ dump as possible because I want you to use simple tools to sharpen your skills. Some GDB commands, we're not going to talk about them, but for you, that's just a reference. When you don't know how to do it, you go to those slides. Okay, so I finished the background part in an hour. Great. Then let's take a break, 10 minutes. Then when we come back, we go into our first hacking. Okay, let's get started. So the second half of this class, we are talking about one of the first discovered software vulnerabilities, which is called stack-based buffer overflow. This is the first. We're almost the first to discover the software vulnerability, and also this is the first vulnerability we are going to look at. So we will spend several weeks on this one, moving a little bit slowly, because also along the way you need to pick up reverse engineering, pick up how to use those tools. So we will move slowly with this one. Then in the second half of the semester, we will move a little bit faster, covering several different types, more advanced attacks, more complicated vulnerabilities. So I will talk a little bit about the history of stack-based buffer overflow. We will go through what kind of information a C program, a C function needs to run. Talk about several C calling conventions. Today we will only look at how to overflow some local variables. Next week we will look at how to overflow return addresses so attacker can execute arbitrary code. You probably heard this term before, RCE, remote code execution. So we are going to say how those work. There are several complicated cases for overwriting a return address we'll talk about in the next few weeks. Okay, so the objectives of this include, first of all, you need to understand how stack works in Linux. This also applies to other operating systems, other architectures. But in our class, we use Linux, we use x86. Like I said many times, in my research, I actually work on ARM systems. Also x86, but mainly ARM. Also, giving you a C code, giving you a binary code, you need to identify a buffer overflow vulnerability there. And eventually, you will also write exploits to as an attacker to exploit that vulnerability. That's the goal of these sessions. A little bit of history of buffer overflow. So buffer overflow was discovered back in the 80s, so 35 years or even longer, that time ago. So right now we don't really know who discovered this first. No one can figure that out. But there was one famous incident back in 1988. So there was a student, his name was Robert Morris. He was I'm not sure he was a graduate or undergraduate student at Cornell. So he developed one of the first computer worms and distributed that through internet. That time the internet was small, and I don't know, maybe he brought down maybe half of the internet at that time, half or 10. So, and the technique he used is the buffer overflow is one of the techniques one of the attack vectors he used there. So this Robert Morris, right now he's a very famous guy. He's a full professor at MIT, I believe. He's an ACM fellow, so one of the titans in computer science. He also has a lot of startups. You guys heard of there is a very famous investing company in Silicon Valley called Y Combinator, whatever. Yeah, he is a co-founder of that. So he's one of the top guys in computer science. So before all of that, he was convicted crime because of this, criminal for this. Okay. So that was back in 1988. So even that time, buffer overflow was kind of like dark magic because not many people know how it works. There are not many tutorials documenting how to do this until 1996. Someone called Alpha 1 That's obviously also a pseudonym. But if you Google, you can find out who is alpha1. Okay. So back that time, he published this more like a tutorial on a hacking magazine called Frag. So a lot of attacks, they were first published in this online magazine called Frag. This magazine still exists, but it's just not as important as it was 30 years ago. Okay, still exists. So this alpha1, this is the very first well-documented tutorial on how to do buffer overflow. So this is a classic. You need to read this as a part of your homework. So I took the screenshot from MITRE Common Weakness Enumeration back in 2009. So this is a list of the security vulnerabilities, most popular security vulnerabilities we have right now. And you can say buffer overflow is still ranked #1 back in 2009. We actually will talk about a lot of those vulnerabilities on this list. So the first one is more like a buffer overflow. Then let's say this one is like a buffer out of bound read. That's a buffer over read. Use after free, we will talk at the second half of the class that is related to how heap works. Integer overflow, we will cover a little bit. Cross-site forgery attack, that's for web security. We're not doing web security in this class. Let's see what else we have here. In privilege management, you can see some of those vulnerabilities, they are combined together for real-world exploits. For example, if you want to hack the kernel, then you probably want to use a buffer overflow to trigger a privilege escalation, something like that. So to understand how buffer overflow works, especially stack-based buffer overflow, we're first looking at how C function and C++ function works. So what kind of information do we need to call a C function? As a C developer, what kind of information you need? You need to know the name of the function. So the name of the function actually is the address of function. You need to know what parameters you can give to the function. What return value this function will give you. And also the return address. The function, after you call this function, the function eventually returns, right? So that's what a C developer think about how do you call a function. But how about a compiler developer? You're not a C developer, you're a compiler developer. Someone gave you the C source code. How do you eventually change that into binary code, machine code that it can run? So those are the things you need to think about. First is the C function, obviously it has code. That's machine instructions. It has parameters and return values. It may use some global variables. It has some local variables. Sometimes it has some temporary variables. It has return address where it return to, and all of those need hardware support to achieve. And there are some function frame pointers that map to a register we're going to use, and also previous function frame pointers. We will use another register or stack to save that. Okay. So two important variable types in C. One is global variable, one is local variable. Global variables, they are declared outside of a function. All the functions in the program can use a global variable, right? This is the same thing for other programming language, Java, whatever. The local variables, they are declared inside a function and also maybe sometimes inside a block. So those other variables can only be accessed when you are inside a function or block. Then parameters are kind of like local variables for a function. So where are those variables? As a compiler designer, when you translate a C function into a binary, those are the questions you need to think. For hackers like you guys, That's also something we need to understand, because only if we understand how it works, we can find if there are vulnerabilities we can exploit. Here we have a simple function. We already uploaded this into our server. This program is called a global local v, global and the local variables. Very simple program here. You can see we have a main function. The main function has two local variables. I have L here means it's local. G here means it's global. To help you clearly say what they are, there's a global variable I, which is initialized to the value 10. Then there's U uninitialized. Then there are two global variables. Basically, one is a string, another one is a pointer to string. So basically, the two is the same thing. We have just 2 pointers. So here we print out where those two global variables at in the memory address. That's what this program does. Then we print out where are the two local variables are. Then we call another function. The function has two local variables, and in that function we print out, also that function takes a parameter. That function print out where are the two local variables and where is that parameter. We just print out the address. So to do that, we use printf %p. Okay, %p print out the address. %p takes the address as the parameter. That's how simple this program is. So if we run this program on our server, let's say global 32, global local v32. Let's do the 32-bit first, then do the 64-bit. 32-bit, we run this program, and it print out those address for us. And you can see, this is a 32-bit program. The whole address space is 4 GB, which means the address has 4 bytes. Okay, so the highest address is 8F. The lowest address is all zeros. So you can say those two global variables, they are at address 56 something. It's like the first half of the address space. And the local variables, they are all at very high address, or FF. Okay, that's because that's a stack. Remember the memory map I drew you guys? The stack is at the very top, but not at the top. The top is the kernel, right? So, and you can say those are the address of the stack, and even the parameter is also on the stack. So those variables are labels, much different from those two. Okay? So those two are global, those two are local. Local variables are basically on stack. If we do the same thing on the 64-bit version, the result is similar, just the address here is different. The address is 64 bits, so technically it should have, the highest address should have 8 Fs, right? But actually we're not using the full 64-bit address. You can say the stack is at some part like the middle, 7F. The global variables still have the 5. So those are still labels. Those are at a very distant places. So those are the global and local variables. Then, in summary, this is where we store most of the information of a function. The code obviously is in .txt section. We talked about that. Parameters. The example we showed you just now, the P is on stack. Sometimes it can also be on registers. The return value, we put them in EAX or RAX, the register. Global variables in BSS or .bana section, which is the 5.5 place. Local variables, they're on stack. That's why it's FF, 7F, whatever. Temporary variables, also stack register. And what interesting is the return address is also on stack. That is why there's a problem with the return address. The function frame, we're going to talk about this later. So you can see that stack here is very, very important. It stores a lot of information. It stores the local variables, it stores the return address, it stores the function frame pointers. Those are very important data and also control information. So if the integrity of those things got violated, then there is a serious security issue. So stack is a structure we use in all platforms, ARM, Intel. Usually the stack starts from a higher memory address, then goes to low memory locations. Functions, they can push the values, registers, values onto the stack, and they can also pop those onto registers. So there are several registers on Intel to directly support stack. One is the ESP RSP register. I just say them like they are the one register because they are just for two different architecture. One is 32-bit, another one is 64. So ESP 32, RSP 64. So that register holds the address of the top of the stack. So when you do a push something, let's say we push EAX, the value of EAX will be pushed onto stack. So the stack will goes down, which means, let's say using the 32-bit example, which means what happens is first, the ESP value will decrease 4 bytes because we're pushing 4 bytes. That's the first thing. We first decrement the ESP. Then we just store the value in EAX into the location pointed by ESP. That's a push instruction. Pop instruction is opposite. So when we do a pop EAX, so this instruction doesn't say anything about stack, right? Doesn't mention anything about ESP. Syntax-wise, it doesn't. But what it does is, it will first store the value which is pointed by ESP into a register EAX. That's the first thing it does. Then it increments the stack pointer by 4 bytes. So if it's 64-bit, then it's just from 4 bytes to 8 bytes, but the same logic here. There are some other instructions will also affect the stack. Especially important for our class is call and return, but we're not going to talk about them today. We're going to talk about them next week. Let me show you more concrete examples because you have to fully understand how those instructions work. The first instruction we're going to look at is push EAX or push RAX. So this is before the instruction, the system looks like this. This is our stack. This is high address. The top is a high address. The bottom is a low address. The ESP, the register, has the address of this item, which means ESP points to this value here, X. Now we push EAX, what happens is we will move ESP down 4 bytes, then put the value of EAX onto the stack. So whatever is in EAX now will be on the stack. So after this instruction, this is what the stack looks like. There will be one more item on the stack than before. So pop is just the reversed operation. ESP right now points to the value X. After we do a pop EAX, the value X will go to the register EAX. And the ESP will move 4 bytes up to here. Call, we're going to talk about this today, but this is probably a little bit too much to digest today. Well, anyway, we're going to revisit this next week. So call instruction, let's say we can do a call EAX, can be a register, it could also be directly some say the code looks like there's a push one, there's a call EAX, then there's some other instructions after this. So now we're going to execute this instruction, which means the register EIP instruction pointer points to here, right? Points to this instruction. So this is what the stack looks like. The ESP points to X. So after we execute this instruction, what happens is the instruction will first push the next instruction's address to the stack. Right now the instruction we're going to execute is called EAX. The next instruction is pop EBX. We're going to push the address of EBX to the stack. The address of it, not the instruction, the address of it to the stack. Then we're going to change the EIP to EAX. So we're going to execute the instruction at the address EAX. And the stack will have a new item here. The return is a reverse operation of that. Let's say this is what the code looks like right now. There's a pop, there's return. We're about to execute return. And this is ESP right now points to the stack. So no matter what ESP points to, next the value is X. X will be popped and treated as an address and put to EIP, which means we're going to execute code from the address X. Okay? Then also ESP will move up 4 bytes. So that is a return instruction. This is probably too much to digest. We're not going to talk about details of call and return today, but that will be a lot of tricks we're going to use, a lot of attacks we're going to use are surrounded by those two instructions. Enter is just those 3 instructions together, because every function, they usually begin with those 3 instructions. Push EBP, move ESP to EBP. Remember, the first one is the destination, the second one is the source, and subtract some number from ESP. So, because most functions start with those 3 instructions, that's why Intel introduced a new instruction called enter, which is same as equivalent to those 3 instructions. So let's say how this works. The stack looks like this. Z, Y, X, ESP points to this. Then the first step, we push EBP. Then EBP will be saved here, right? EBP value will be saved here. The next one, move after that, ESP will point to here. Then we move ESP to EBP. So we will override the old EBP value. So now so EBP also point to here. Before only ESP points to here. Now EBP also point to here. Then after that we subtract value from ESP. So ESP moves down, EBP stays here. Okay. Well, I have some animations for this later, but now this is how enter works. Leave is basically move EBP to ESP, then pop to EBP. Later, we're going to see more examples of why we're doing this. So now we reach to our next important concept called the function free. So a stack is basically each function's scratch memory. That function puts the local variable there, put a return address there, and those addresses cannot be determined at compile time, because that's a stack, that's not code, that's moving. Also, a function can be called many different times, right? So it's a stack, it's not necessarily at the same place. It's moving, right? So how do we access those local variables? Because their absolute address is moving. That's why we use some offset. And the offset, we need a base. We need a base and offset. And that base, we call it the function free. And in x86, also 64, we use the register EBP to record that base. That's why it's called EBP, base pointer, right? So you can see the hardware is actually tailor-made for the software. Even though here we're talking about software, how do we do this, but the hardware is actually designed specifically for those kind of purpose. So a function string, usually we say it starts from where its EBP points to and ends at ESP points to. When we say more examples, it will be easier for you to understand. Right now, I see some of you are getting a little bit confused. Okay? So, also there is something called calling conventions. Calling conventions determines who will store what information. Whether the caller will store that information, whether the callee will store that information. And those are the contract between callers and callees. And compilers need to implement those contracts. So different operating systems, different processors, compilers will use different calling conventions. We are going to look at two calling conventions today. The first one is called the say declare. This is like the standard calling convention for 32-bit programs in Linux. So what happens in this calling convention is the caller. What is the caller? In that our simple example, we have an add function, we have a main function. The main function calls the add function. The add function returns to the main, right? So the main function in this case is the caller. The add function is the callee. The caller will push the arguments for the callee to the stack. If there are multiple arguments, we push the rightmost arguments first. We push them to the stack one by one. Then it will execute the call instruction. The call instruction does what I just showed you. It will push the address of the next instruction to the stack, then move the destination to EIP. Now, after this step, we are in the callee, right? Because when we call that, we're calling a callee's address. So now we are in callee. Okay. After this step, the EIP points to callee. We are in callee. Then the callee will do the following things. So by the way, the caller itself, at some point, it is also a callee. Main function calls add function. The add function is callee. Main function is caller. But some function will call the main function. Otherwise, how it get wrong, right? So the C library has a function called the libc start main or whatever. Probably that's the name. So that function will call your main function. So at that point, the libc start main is the caller and main function is the callee. So at that point, the main function will also do the same thing. Okay. So back into the add function. The add function is a callee. It will pushes the previous frame pointer onto the stack. The previous frame pointer, the function frame pointer, is the main function's frame pointer. Main function is the previous function, and that is the EBP. So it will push EBP to the stack. What's the purpose of this? It wants to reserve that data. It is going to use EBP itself to show where its own frame starts. But to do that, it will use the register EBP. So it has to reserve what already is in EBP, which is main function's frame address. So it will push that into the stack to protect that. Then it will set up its own new frame pointer, which is just move ESP to EBP. After that, it will create some space for its own local variables. How to create a space? Just subtract ESP with some number. Then those local variables will be in that space. It's just subtracted. Then after it runs, it will just return value in EAX. Okay. This is without example. This is hard to digest, so don't worry. We're going to say more concrete examples. So here, this is the callee part. This is called the function prologue, because most functions, they will start with this. Just those three instructions. Push EBP to reserve the previous function's frame pointer, then move its own frame, then subtract some number from ESP to reserve space for local variable. And this is called the epilogue, also 3 instructions. Move EBP to ESP, because at this point, we don't need ESP anyway. Okay? We don't need ESP anymore, so we're not saving ESP. We're directly overwriting ESP. By moving EBP to ESP, then we pop EBP. What is pop EBP? Pop EBP is to restore the previous function's frame. Because pop will pop whatever ESP points to. ESP at this point points to the saved EBP. Then it's just a return. Go back to the main function. Okay, let's look at the same function, and we're going to look at the. Okay, we're not ready to look at the code line by line. Let's say what we do. This part we already look at, so we can skip this one. So this is my hand drawing of the stack. We can skip this for now, and I was using AT&T syntax before, so this semester I'm switching everything to Intel syntax because all other platforms on x86 we have the choice of using Intel or AT&T syntax, but on other platforms if you are using ARM, MIPS, usually there is only one official syntax, and that syntax look much more similar than the Intel syntax. So if you are familiar with Intel syntax, it will be easier for you to switch to other platforms. But the AT&T syntax is a little bit much different from. That's why I'm teaching this one. Anyway, let's say one concrete example first. This one. Okay. This function, this program, we are going to calculate the factorial of a number. This is the main function. The main function take the argc is 2. We want the argc to be 2, means we want you to input something. If you do not input, we will print out the usage. Whatever you input should be a number, so we change that number into an integer. Then we just calculate the factorial of that number. For example, you input 2, then we will just calculate 1 times 2. You input 4, we calculate 1 times 2 times 3 times 4, right? But we are writing a recursive function to do that. The function is called fact, and it takes one parameter, and it print out. It first print out the. This is just a string. Print out the string, but print out the number we are calculating. Let's say we want to calculate factor 4. So what we're print out here? The first time we print out in factor 4, right? Later, we'll print out the address of this parameter, which is 4. Then if this number is not 1, we return 1. Otherwise, we call this function again. This is a recursive function. We call this function again, but get a minus 1's factorial. Then use that times n. So if we call factor 4, what happens is the main function will call factor 4. Factor 4 will call factor 3. Factor 3 will call factor 2. And factor 2 will call factor 1, which returns 1. Now after that, we times things together. So what we want to say here is what the stack will look like. Because here we print out the parameter's address. So what do you expect this will be? This is the same function, right? But we call this same function 4 times. The stack will go up or down. The stack will go down, and the address of this n will go down, right? So if we do this one, let's try this on the server. Factorial 32. Let's do this one. Okay, let's do a small number like a 4. Let's just do 4. Okay. So we run this program. The main function calls factor 4, and the parameter's address is D680 hex value. Then fact4 calls fact3, and the parameter's address is 660. Okay, it's 32 bytes lower. Okay, because this is hex, 20 is 32, right? So this is 32 bytes lower. Then this one is another 32 bytes lower. This one is another 32 bytes lower. Again, so from this one you can say clearly the stack goes down, even though this is the same function. Okay, that's why you cannot determine those address at compile time, because you can call them many times, right? The local variables, they can be anywhere. Another example to show you. So this example shows you that this parameter is stored on stack, and the caller put that parameter there on the stack. The next example, we have 5 parameters, and just add those 5 parameters together. Like the calling convention I told you, this is a 32-bit machine. What happens is the caller is supposed to push those values onto the stack. Okay? So the caller, which is the caller? Main function of the caller. The main function is going to push 5, 4, 3, 2, 1 to the stack. And that is the order from the rightmost to the leftmost. So we can say the disassembly of this. Five parameters, 32. We do a obj dump. We use entire syntax. So you have to use hyphen uppercase M, means the machine we are using is Intel. Then D here means disassemble. We want to disassemble this program. And we are looking for the function func, right? I think that's it. Yeah, func. That's the function we are looking. So we should look at the main function first. Where is main function? Oh, here is main function. Oh, this one optimized away everything. Hold on. Looks like this one optimized away everything. Oh, it's not. It's here. That's weird. What's going on here? So, yeah, sorry about that. This one is not what I want. But I can explain you what happens here. So you can see the C code of this. This program, what we're trying to do is we want to calculate the sum of those 5 numbers, right? But we're not outputting it. We're not really using it. And the compiler finds out we're not really using it. The compiler just optimizes that part away. So you back to the code main function here. So the main function, by default, it returns 0. So the compiler just make EAX 0, then just return. It optimizes away the whole part. So that's why we're not saying that. But it does leave the function func here. From the function func, let's say this one here. We can still say how this function is never called in this library, but you can say how it works. Let's say ESP plus 8. That is the first argument. The first argument is moved to EAX. The second argument, let's say, ESP plus 4 is the first argument, plus 8 is the second argument. Anyway, those are the 5 arguments. They are added to EAX and return. Okay. So this one shows those arguments are actually passed on the stack. I should change that program a little bit. Yeah, this part is interesting. The compiler actually optimized that away. We're not calling the function func. Yeah. I think that may be different from my no-code program. Let's see. Let's see. Oh yeah, my local program is also, that one is optimized away. Let's say, what do we do? Let me change this really quick. Sorry about that. So we change this really quick. So what we need to do is we return this. We return this, okay? Previously, we're not using the value. Now we just return this. So the compiler has to calculate this. So it can still optimize this, but let's see. What is make here I'm using? Make FP. Okay. Oh, I'm using optimization level 2. That probably also be the problem. Should not use that extension. So the compiler still optimizes it. The compiler just calculates the value. It's f, and just return it. I need to change the make file. Sorry about this. Sorry, it works. Let me change the make file. I think that's because of the optimization level here. I'm using O2. I should use O0. Okay. I wish it works this time. Where's main? Let's see main here. Oh, good. Now we have it. So you can see, now I change this, the main function. This is a caller. The caller will push all the values. It works first to push 5. Then 4, then 3, then 2, 1, right? Push that here. Push 4, 3, 2, 1, then call the FP, right? So that's the caller's job to push, then we'll make the call. Then the callee will use the ESP plus something to retrieve that from the stack. So that is the 32-bit version of the calling convention. That is not the only calling convention. You can say one of the problems with that calling convention is every parameter you want to set, you have to push that to stack. Stack is memory, which means it can be slow. So that's why there are other calling conventions. There is one called the fast. So for example, if you define your function like this, you add an attribute, a fast call, then the compiler will generate a faster version of this program, which means the compiler will use the first, will use the register ECX for the first argument. So the previous example I showed you that the compiler pushes, the caller pushes all the parameters onto the stack. If we go to the faster version, I hope this one works. Let's say, hold on, why are we doing global? Should be 5. Oh, sorry about that. I think TM made some mistake here. Let's see if I have a local version, I can show you. Local version I don't. Let's go to this one. are looking for the main function, and the main function calls which one is the call? Oh, here. You can see this is a previous function that we call func with a p, the address. And the caller didn't push. There's only one parameter. And the caller didn't push that. We do not say a call push here. Instead, the caller moves that value to ECX. So this is a faster approach because you're not using memory. Because memory is slow. This is totally on CPU, not on memory. So you can see that's the 32-bit version, and the 64-bit version, because we have many more registers, the calling convention has changed a lot to make the program much faster. In 32-bit, we push those 5 things to stack, and in 64, we are going to simply put the first 6 parameters into those 6 registers. So it will be much faster. If you have more than 6 registers, we are going to use stack. 32-bit default, we're using stack. So 64-bit version, let's see which, let's say still 5 parameters, this one. Yeah, unfortunately, main function also optimized it away, but we can look at the func. Look at the func. It's not accessing from the stack anymore. It's directly using those registers. Okay, I'm going to update both programs to make sure the main function will actually call that. Anyway, those are the calling conventions for that. Okay, finally, we are ready to talk about our first attack. So in this attack, we are going to overwrite some local variables on the stack. So this attack, we are not changing any control flow data. We're only changing some regular data. So this is our vulnerable program, left-hand side, our vulnerable program, right-hand side is the disassembly of this vulnerable function. Let's say if we can identify the vulnerability here, we have a main function. The main function looks for 2 arguments. One is in argv0, another one is in argv1. Argv0 is actually a program's name, so that's the part we do not control. And if you run the program, what your input after the program name will be in argv1, and that will be given to the vol-foo, which is a vulnerable function. The vol-foo takes 2 arguments. One is an integer, another is a pointer, so which is basically a string. The second part is a string. The first part is an integer, and the integer is hard-coded. It's not really used here, hard-coded. What we can control is this. There is a local variable j. J is initialized to I, which is 0. So when this function executes, j is 0. After that, there is a buffer, 6 bytes buffer. At the C code level, this is 6 bytes. At the disassembly level, version code level, not necessarily. The compiler doesn't have to give it this 6 bytes. The compiler can give it 16 bytes. As long as it's bigger than 6 bytes. The compiler can give it 32 bytes. Maybe by giving the 32 bytes, the program will be even faster for alignment reasons, right? So after that, there is a string copy. So who used the string copy before? Yeah. So what string copy does is to copy a string from the second parameter to the first one. So you can see the second parameter is p. What is that? That's our input, right? The problem string copy will only stop when you reach a 0. But the buffer is only 6 bytes. But we can input more than 6 bytes, right? So why will that happen? That will cause an overflow. So we need to figure out what we are going to overflow this and how we can exploit that. Then the program keeps running, it checks the value of j. We know at this point j is 0. We initialize it to 0. If it's 0, it will just go to else, then print IP to the full. If it's not 0, it will call print flag, which will retrieve the flag in the file system and give us the flag. Okay? So that is the program. So let's run this program. Let's just do the 32-bit version. So this is in the buffer overflow category. Go to overflow 1, 32-bit. Okay, so this is a program. If we just run this program, what will happen? Nothing, right? If we just run this program, it will check if we have 2 arguments. No, so it will just return. Nothing happens. If we give it some string, like I give a 4 character here, it will just show IP to the full. That's it. Okay. So then let's look at the disassembly of this line by line, try to figure out why there is a vulnerability. Before that, let me explain how string copy works. Some of you probably not familiar. This is just how string copy is implemented in most libraries. It will just copy from the second parameter is the source, the first parameter is destination. It will copy the string from the second to the first. It doesn't care how big the first buffer is. It will only stop when it reaches the end of the second string, the source string. And at C programming language, a string stops when there is a 0. Otherwise, it doesn't stop. Okay? Of course, I mean, some good programmers will write code like this. Okay? I actually saw this implementation from one of the Linux inventor, Linus. He actually he showed this implementation in one of his slides. He says, if you are C programmer, you should always write C code like this, not like this. Okay. Anyway, they are the same thing. Okay. If the compiler is smart enough, it probably will generate the same code anyway. Okay. So let's look at the disassembly one by one, 9 by 9, and also I have the stack here. Remember, we are about to execute this line. This function, Overflow, is called by the function main. So the function main already pushed 2 parameters onto the stack, right? The function main already pushed 0 and this pointer, this string's address onto the stack. That's why on the stack right now, we already have the P, which is the address of the string. Then we already have the I, which is 0. Okay? Then it's a call instruction. What does call instruction do? It will push the return address onto the stack. So now the return address is onto the stack. ESP points to here. EIP points to this one. We are going to execute this one. Okay? Now, okay, consider yourself is Intel CPU. And let's say one will happen. The first instruction, push EBP. So we're going to push. So the first, what I draw the right hand side is the result of this instruction. Okay. So the first one is push EBP. Oh, I didn't open my microphone. Can you guys hear me? Okay. Anyway, so the first instruction is EBP. So EBP will be stored here. we call it the old EBP. After that, we move, so the ESP were points to the old EBP, right? So after that, we move ESP to EBP. So both ESP and EBP were points to here now, right? After that, we subtract 18 in hex to ESP. So EBP stays here, ESP moves down here, and the distance between ESP to the saved EBP is 18, which is, how many is this? 24, right? This is 18 in hex, so it's 24 decimal. So it's 24 bytes here. This part is 24 bytes. Then we move EBP plus 8. We move the data at EBP plus 8 to register EAX. What is the EBP plus 8? EBP is here. EBP points to the old EBP. EBP plus 4 is the return address. EBP plus 8 is the first argument of this function, which is 0. Okay? So after this instruction, EAX will be 0. Then the next instruction, we move EAX to EBP minus C. C is 12, right? Okay. So what we're doing is so EBP minus something, like I said before. This is the local variables. So that address, EBP minus C, is actually the local variable, what do we call it? Local variable J. So this instruction, what it does is to assign the value of I to J. So after this, EAX will be 0. The local variable J, which is at this address, will also be 0. Look at the C code here. This is this part. Assign I to J. Okay? After that, we will subtract ESP further. So we get more space for this local variable. But we know that from ESP to the saved EBP is 20, which is 32 bytes. Because here we have 18. Previously we have 18 in hex. Now we add another 8 in hex. Well, I mean, 8 in hex is the same as 8 in decimal. So that would be 32 in decimal, which is 20. So now this part is 32 bytes. So after that, we push EBP plus C, which is the second argument. We retrieve this piece value. We push that into the stack again. Why we are doing that? Because we are going to call the function string copy. And we are setting up the parameters for string copy, right? And a string copy takes which parameter? The string copy takes P. The first one is P, the second one is buffer. We don't know where buffer is, but we know what P is. P is this EBP plus C plus 12. Yeah. Then after that, ESP points to P, which is the same here. After that, we will load effective address EAX EBP minus 12. I said this before. This is basically moving EBP minus 12 in hex to EAX. So after this, then EBP is here. Remember, EBP is here. The EBP minus 12 will be somewhere here. And that address will be moved to EAX. Now EAX has the address of the first argument, which is a buffer. So what will it do next? It's going to call string copy, right? It has to put the 2 parameters for string copy onto the stack. So it's going to push that one onto stack. So now we have the parameters for string copy here ready. The first parameter is the address of the buffer. And the buffer itself is here. The second address is the source of the buffer. Now we call this function string copy. Okay, we do not go into the function string copy. We can, but we're not going to do that. So here, the string copy, what will happen? String copy will start writing from this buffer address, right? That's what a string copy does. The string copy will copy a string to your destination, which is then this address. So if your input is smaller than 6 bytes, what will happen? The string copy will write things here, inside the buffer. What if your input is bigger than 6 bytes? What will happen? It will overwrite the local variable j, right? It overwrites this one. When it overwrites this one, the j's value will be changed. J's value will be changed. And if you go back to the source code, when j's value is changed, it's not a 0 anymore. It's going to print the flag for us, right? That's the logic. That's the vulnerability here. So let's say after we call this, we could override this. Actually, we can even override everything above this, including the return address, everything. That will cause a segment fault. Because eventually the program, eventually this is a val foo. The val foo will return to main. And this address is supposed to be an address inside main. But we overwrite it with some garbage, then it will return to some garbage address. There may not be valid instructions. So it will cause a segment fault. But before that, we still get the flag because we print out the flag. So after the call, the caller, in this case, the val foo is a caller, string copy is a callee. The caller will balance the stack by adding ESP by 10. So ESP will move up. Then the caller will compare 0 with that local variable j. It will compare to try to say if j is 0. So this instruction here, the compare, CMP compare, EBP minus say that's local variable j, that's hard-coded 0. This instruction is basically this if here, okay? This if you know say this, or any programming language, you know this one checks if it's 0, okay? So if the value is 0, it will jump equal to somewhere. It will jump to maybe, I don't know, somewhere. Anyway, if it's not 0, it will just call print flag, right? Okay. So how do I print out a flag? Any idea? How do I print out a flag? What? Okay, so right now I'm giving 4 bytes. If I give 6 bytes, that work? No, right? This one is actually interesting. 6 bytes. Why give 6 bytes? Because it's a string copy. The string copy eventually will append a 0 there. So when I give 6 bytes, it will put the 6 bytes here. Then it will also put a 0 here. But the 0 doesn't change the value of j. So it will not give us a flag, actually. So when we do this, it will not give us the flag, even though we actually override j, but we're overriding j with 0. So we just give 1 more byte. Doesn't matter what it is. It can be anything. You print us the flag. Make sense? Doesn't matter what this is. It can be anything. Ooh, cannot build this. That's a special value in shell. Yeah. Okay. Anything, because now we change it to non-0, right? Okay. What if we give it more? Like I said. But so when we give it more, it will override all of those. It will still print out the flag for us because it will still call this. But when this function returns, it will return to main. It will require this address. And that is a garbage address. So that one gave us the segment fault. But before that, it already gave us the flag. Okay? It gives us a flag, then give us a segment fault. So that is how this one works. The 64-bit version, the same thing. Let's say buffer overflow 1, 64-bit version. the same thing. I'm not sure the offset here because maybe the same. This is 6, 7. Oh yeah, the same. Yeah, 64-bit version the same. So this is a very, very simple example. So we still have 40 minutes. So in the next 40 minutes, I want you to crack this one, Overflow local 2. Yeah, this is also part of the homework. So I'm basically giving you 40 minutes to do your homework. Okay. This one is almost the same. The only difference is J cannot be any non-zero value anymore. J has to be a specific value, which is this one. You have to give J this specific value. You can start with a 32-bit, then move to, after you finish that, you can do 64-bit. Some tricks here. If you, so here on our server, you should use Python 2 actually. In this syntax, you need to use Python 2. Let's say you want to give this program some input, but this input is not human readable. So you have to give a hex, use this syntax. You can, here should be Python 2, because Python 3's syntax is different. This one, the default one, if you run on the server, it will be Python 3. You have my slides on my website, so you can have this. You can know the syntax here. Okay, let's work on this one. Let's say, you can also try the Overflow version 1 first. That one is easy, then you move to this one. Oh yeah, that's probably using Python. Yeah, you should, yeah. Python 3 thing. I'm not familiar with Python 3, so Python 2, yeah. No. The program name should be the. Yeah. Yeah. Or maybe just to move to another place. let's say, okay, good. 2 solved it. 2, yeah, we can see here. 2 people solved it. Good. Let's see how this one works. Let's see. We can use the same stack here, right? So the Overflow 2 and Overflow 1, they're basically the same program. The only difference is, what's going on? The only difference is here, J changed to J equal to a specific number, okay? Then let's look at the stack here. So if we want to do that, where is the local variable J? Local variable is J is here, okay? Where we start overwriting is the buffer. Same as the last one. So whatever we input, the first 6 bytes of that will go to buffer. We don't care about the value of buffer. That 6 bytes can be garbage, doesn't matter. After the 6 bytes, the 4 more bytes, because J is 4 bytes. After the 6 bytes, 4 bytes will be J. And that 4 bytes has to equal to that number, 1, 2, 3, 4, 5, 6, 7. That's it. So how do we do this in the command line? Is we go to, okay, create here. So the first 6 bytes. Let me use Python to do this because the character we're generating will not be ASCII. So this is a syntax. So let's say we do A times 6. Is that the correct syntax? Python 2, oh, no, should be here. I think should be this one. Yeah, this is the right syntax, right? So I use Python 2. I'm going to print 6 A's. I will use this syntax. So if I want to print 6 of 1, 2, hex value 1, 2, I will do this. Well, obviously that value is not human readable, so we cannot say it. But if we pipe this into XDD, we'll be able to say that's the value I put there. 1, 2, 1, 2, 1, 2, 1, 2. Okay? So each 1, 2 is 1 byte because this is a hex. This is 1 byte. Okay. So go back to here. What we want to do is we can put, this is the correct syntax. We can put 6A there. We put a 6A there. So what happens is those A's will fill that buffer. Okay? We can do 6 B's, 6 9s, whatever. Because this is ASCII. This is 1 byte. This is also 1 byte. This is a hex. Okay? This is ASCII. This is hex. So, but we're not really overwriting the J yet. We're only overwriting the buffer. So that's why after this, we need to add more things. After those 6 9s, we need to add more things there to override J. So what do? We need 4 more bytes. Let's say if we do 1, 2, 3, 4, 5, 6, 7, 8. Will this be correct? Let me see. This will be the lower address. So no address go to lower. This may not be correct, right? Because the endianness. Because of the endianness. This is the lower address. When you put this is a lower address. So lower address will be the least significant byte of that integer. So what I'm writing here is actually 78, 5, 6, 3, 4, 1, 2, right? So we need to reverse that. 78, 5, 6, 3, 4, 1, 2. That's how we get a flag. Make sense now? So the line, this 6 bytes of buffer, the padding, the fading, doesn't really matter what it is. It can be whatever you want, right? Because we're not going to use that anyway. They are fading the buffer. The key is these 4 bytes, what you put there. And because of NDNS, this is this is the high address, the 12, the high address. The high address should be the most significant byte. So that's why the address we have is here. This is the most significant byte. That. Okay, makes sense? Okay, cool. This is our first hack. Next week we're moving to something a little bit more difficult than this. So that's why this week, get the homework done. If you do not understand what's going on here, debug this program. I see some of you are debugging. That is always a very good habit. Okay, just debug step by step. Try to understand what the CPU is doing. Okay, cool. I will upload the homework tonight. See you next week. Okay, like I said, you should not. Let's see.
I thought it's using Intel syntax.
No. GDB Intel syntax. Why? Oh, you can set the syntax flavor there.
Oh, I see.
I probably already said that before. Yeah.
Okay.
Set. Yeah.
Okay. Sounds good. Thank you very much.
Just Google. Like I said, Google.
Okay. Thank you.
Yeah, sure.
You guys can go ahead.
Well, the reason we use Python, you can see those characters. Like what, right? That doesn't map to any ASCII you can type. For example, if it's A, it happens to be like A probably. Then you can type it. This is not something you can type. Yes. of the reasons. The main reason is that, let's say, if I set it apart, in that case, then you don't have to replace it. You just type ABC. But what I said is 1, 2, 3, 4. That doesn't match with any ASCII. Let's say ASCII.
Yeah. Yep.
You get what I'm saying, right?
Yeah.
You go to ASCII table.
So there's two reasons on why
yeah.
you use Python there. Okay.
Yes, and like ASCII, like see, I don't know what this is, but anyway, it's not a character you can input.
So then even if you were to ask it to this, because when it overflows, it's only going to go one by one, right? It's only going to overflow this, and then that's going to be the value for j, and then it's going to do this one next.
So you can think this.
So when you did Python, you can put them all together, right?
Not really. So for example, I'm doing this. It will be the same as I do this.
Okay, so that's making it all separate instead of one.
Yes, but it doesn't matter. They're the same thing.
Okay. Because I tried. Because it's not.
There is an onionness,
I get it.
right?
Okay.
Yeah.
So if you did do okay, that's why it didn't work before, because what you were saying with the ASCII, nothing correlates to the ASCII characters
Yep.
here. But if you had ABC,
Yeah.
then you could do, just 6 of these and then the ABC.
Yes. Yes. But also there is other things, onionness.
Right.
Because
So
this is
then
a
the
little
other-
onion machine.
Right, the other way. Okay.
Yes.
And then I did have a question. I was one of the people that had the extension poll, which
Oh,
I thank you for giving me
I see.
first of all, because how it
So
worked out, we were.
one of you are Alex, right?
Yes.
Alex,
I
and
see.
then I'm
Yep.
Jake.
You guys are undergraduate or?
Yeah, or undergrad.
Okay.
Jake
We
was-
actually have another hacking session. We do all kinds of hacking.
Okay.
It's Friday afternoon, 3 o'clock. If you guys, I'm recruiting undergraduates to do that. So, well, I mean, if you guys want to do that, it's also okay. But I'm not really advertising too much.
Okay.
Yeah.
So from there, we're doing something even simpler than this. Starting from, because I'm recruiting freshmen.
Okay.
Okay.
Oh, okay.
Yeah.
So wait, Friday at 3
Friday
o'clock?
at 3
Shoot me
o'clock.
an email. I'll add you guys to the Slack channel. Yeah.
Yeah.
Okay, great, thank
Yeah,
you.
awesome.
And then, so one of the questions I had was, when you say the instruction, just kind of what you mean by instruction, do you want the explanation for just what the instruction does, or do you want just like the specific of what address it goes to and everything? Because I just have what the instruction does.
Okay.
Is that
From my point of view, I'm not going to read all of that, right?
Okay.
So I only need something high level.
okay? So just what the instruction
Yes.
does. Okay.
But you need to make sure you understand, right?
Yes.
Yeah,
yes,
we'll go
yes,
through
yes.
it and understand.
And then the other thing I had for finding the set UIDs when I
There is no set ID. There's a set GID.
GID. So
GID is
so
okay.
the GID works, and then this would be my GIDs.
Yes.
Correct? Okay.
Yes.
Great.
GID would be
Thank
fine.
you.
Yeah.
Professor, I have a question how, after reversing this one, how it's work? Like, could you please explain, more
So-
details,
so-
more practical, like how
So
this works?
J has 4 bytes. Okay. This is low address. This is high address. So those are 4 bytes. Alright. You are putting things 6 of n garbage here. Let's say we have a times 6 put in here. Now after that we put. So first of all, what is the value we should put here? The value here should be 1, 2, 3, 4, 5, 6,